Think about this. Per one bird, how many girls do we get on average per one bird? Look over there. 90% of a girl, right? 0.9. So if you add another bird, on average, that bird is 90% girl. So you're adding another 0.9 in, which would have to be 1.8, which is the same as 2 times 0.9. Yes, that has to work, doesn't it?
Okay.
What you've just discovered, my friend, this is why we have distributions of probabilities by special names. There are special cute little formulas to calculate their averages. Do you have to know them for this class? No. Because of what I just gave you, some of you guys, I'll give you the rest of the guys as I wander around class in a minute. You don't have to memorize these formulas, but they all do have very special formulas to calculate things like averages. So yeah, you just discovered it. Nice job, my friend. That's why I said, I picked on Raphael, I said he could figure it out, because he already figured out that it's 9 girls per 10, which is the same as 0.9 per 1, which is the same as what per 2? Simple ratio. So just double everything. Which you just figured out. Basically, you discovered that for a binomial, mu equals n times p. More on that on Wednesday, but not right now.
Yeah,
Didn't even see that.
Double time.
Exactly. You double the average for 1, which raises it. It keeps the same ratio. So the same slope, but you're further down the line. Cassie, go ahead.
If you added another bird,
Which we're about to do.
Okay, never mind.
Yes, which we are about to do, my friend. You got it. You got it. I want to keep building the flock. You ready? Let's build the flock. Let us now add Marge the Americana. She's the one that lays the cool little Easter eggs. She lays the little green ones.
She lays green eggs?
She does. Totally rad. You guys have Americanas in your flocks? Yeah, they're awesome. They're awesome. She also gets picked on the most, but she can hold her own. She can hold her own. She's good. She's good. She's fast. She's loud, too. She's what I thought was a rooster for the longest time. At 5 a.m. I'm like, what the hell? We did get a rooster. No, we didn't. Unless roosters can lay eggs. Anyway, so here's 3. New flock, 3 birds. So Max has gone in and pulled 3 birds. Let's swing over here. Sideboard. Ooh. Let's see. It's actually visible. Just keep pulling it. Just keep pulling it. That's probably first. That's enough. Oh, God. Need the video editing staff. Oh, that'll work. All right, flock number 3. 3 birds. I still want to know how many girls I have. I still care about that. Number of girls. What are the values of my random variable this time?
0, 1, 2, 3.
Absolutely, Shelby. Absolutely, you guys. 0, 1, 2, and 3. Has to be, right? Has to be. Has to be. And I want to know the associated probabilities with these things. I want to know the associated probabilities. What is the chance if Max goes in there and grabs 3 little marshmallow peeps, puts them in the box and walks out, that they're all boys? Yes, Shelby, perfect. Because in order for them all to be boys and none of them to be girls, that means I've got a 10% chance that Bertha is a boy, and a 10% chance that Marge is a boy, and a 10% chance that Nancy is a boy. Which means I've got a 1 in 1,000 chance they're all boys. Do you see? It's getting harder to get all boys exponentially with each additional bird. It was 10%, then 100, then 10%, then 1%, then 0.1%. It's getting exponentially harder to get all boys. It's also getting exponentially harder to get what? All girls. Let's jump down to here. In order for them to be all girls, I have to get the 90% of the time that Bertha is a girl times the 90% of the time that Marge is a girl times the 90% of the time that Nancy is a girl. 729?
Yeah.
Check me on that.
Yeah.
Thank you. Notice there was a 90% chance when I only bought 1 bird that I had a girl. Then it went down to 81%. Now it's down to about 73%. Fair enough? Yeah, it's getting challenging. It's getting challenging because every time you buy another bird, you're rolling the die again. Who said flipping a coin earlier today? That was fantastic. Flipping a coin, or 50%. I believe I heard 50% earlier today. This is flipping a coin, isn't it?
Yeah, pretty much.
It is, except the coin's not evenly weighted. The coin's not 50-50. The coin is 1090, right? Do you see the distributions? Are these uniform distributions, friends? They're highly skewed. Highly skewed distributions. Look at the weights. It goes from very unlikely up to more likely, and the highest likelihoods are at the bottoms. That's because it's a coin flip, but it's not an equally distributed coin flip, not uniform anymore. Awesome. Fair enough? Okay, let's figure these two out. What makes these two challenging to find out now?
Now we have three that we have.
Yes! Son of a, now we have to figure out, you know that this plus this is 73%, right?
Mhm.
That's 73%. So these two here have to add up to 27%, right? But there's two different ones. How are you going to figure them out? What do you think? What do you think? What do you think, Shelby?
I just was curious, can you still do three, and then parentheses,
Do you like this idea? Well, first of all, can we start with the point ones and the point nines, Shelby?
Yeah.
So let's start with that. I like this, my friend. So we're going to get one girl, which means we have in the background what else? Two boys. That's what makes it binomial. You got two boys and a girl. So we've got a boy, that's Bertha, another boy, that's Marge, and a girl, that's Nancy.
But don't you have to do that sometimes?
Have to, don't. That's what Shelby's saying too. Don't we have to triple that? Because what did I just say? I just said Bertha's the boy, and Marge is the boy, and Nancy's the girl. But can't we get another girl a different way?
Yeah.
Couldn't Bertha be the girl?
Yeah.
Or couldn't Marge be the girl?
Yeah.
So we have to triple this. We have to triple it to count for all three positions of that girl. Either Bertha or Marge or Nancy. So .009, check my math on this one, friends. 027?
Yes.
I think that's right? Yeah, 27, the decimal point. Is that fair? You guys buy that logic? Can we do a similar thing for two girls and a boy?
Mhm.
I think so, right? We have a boy, so let's make Bertha the boy, and then make Marge and Nancy the girls. But that's assuming Bertha's the boy. Who else could be the boy?
So we multiply by three.
Marge or Nancy. So once again, Cassie, it's got to be
Multiplied by three.
multiplied by 3 again. So we got 0.81, 0.081, 243. Check my math on that one, friends. Is that right? No, that's not right. I got to carry something. Oh, that is right. Point.
0.243.
Yeah, that is right. I didn't have to carry anything. We're good. Actually, I can check to see if I'm right now. I know these two sum to 73%. These two have to sum to 27%. Check that out. They do. They do. So the whole thing sums to 100%. The whole thing sums to 100%. Yay, which means it's a distribution. Because I got quantitative, discrete, disjoint data over here. I've got cumulative probabilities over here. Yeah? Good so far?
Yeah.
So the big question, of course, as it always is on average, how many girls do I have?
Multiply.
And I believe Cassie already figured this out for us, didn't she?
Well, no, you just have to, well, you have to multiply it, but I was just wondering, is it 1.8 plus 1.8, or is it 1.8 plus 9.9?
We're adding how many more girls?
1.
One from the previous flock. Every time we add a girl, how much more girl on
0.9.
average do we get? 0.9. So it's 1.8 plus
Okay.
0.9 to get 2.7.
Yeah.
Now, if you don't want to remember that, could you just run one bar stats on this bad boy?
Mhm.
Of course. Or you could do 0 times that, plus 1 times that, plus 2 times that, plus 3 times that, and sum it everything up. But your first comment was the greatest thing. Is it 1.8 plus 0.9 or 1.8 plus 0.8? Well, it's 1.8 girls per 2 birds plus the 0.9 girls per 1 bird altogether
That's what's happening
is
also.
exactly. It's 2.7 girls per 3 birds.
Gotcha.
So there's a constant ratio. Every time you add a bird, you're adding 90% more female of a female to that pot.
I love this terminology. It's good.
I swear, Cassie, I was so stoked when I stumbled upon this because for years I was doing all kinds of things to introduce the binomial, and finally I stumbled upon this, and this sticks with students. I can always refer to chickens.
No, this makes sense.
It does because it's something tangible, something you can relate to, but also it's something that it tugs something in your hippocampus. Like in 244, if you guys have me for 244 later, I'll refer back to the chickens, and you'll be like, oh God, yeah. Two-sided coin. Oh, yeah, it's two-sided coin. It's a damn chicken coin, 90-10. You'll just remember that. For some reason, it's just episodic. So very, very glad we come up with this. Okay, last but not least,
4 birds.
it's time for 4 birds. Let me go over that side because I'm running out. That's not going to be very visible. Carry my ghetto rig over there.
Yeah, at least you wheel one or something.
What's that? Well, if I get the, oops. if I figure out that cool carriage I showed you guys, the Lego thing that Neo Max built, that is going to be awesome. But I need a few more hours in the day to do that.
Shannon, we're doing 4 birds.
Yes.
On average, the next is going to be 3.6.
Beautiful. Thank you. Thank you, Shelby. Shelby already has the average for 4 birds. So now let's swing this around. Behind Shelby, I don't want to run into you. There's my 4 birds. We've now added Mary in. Mary's the Delaware. FYI, these are named after mine and my wife's grandmothers. So Mary and Bertha, the top row, are my grandmothers, and Marge and Nancy are their grandmothers. Great names for birds, and they fit them. What's hilarious is my 2 will hang out together, and so will her 2. Like on average, I see more of the time, Mary and Bertha hang out. It's like Salt and Pepper from the 80s. It's great. Totally great. Totally great. Totally great. I don't know why. I have no reason to think that they should, as you're about to see why. There's a 1 in 6 chance of that happening, and you're about to see why it's 1 in 6. All right, so we're over here now. Okay, so now Shelby has already come up with the average number of girls per flock force. So flock number 4. Finally, we are at Sean's flock. 4 birds.
3.6
Yes, on average, the average number of girls is 3.6 girls per 4 birds. So once again, we've just added one more 0.9 into the mix. It goes right to have what you said earlier was great though. 4 times 0.9, right? 4 times point. That's what you said earlier. You can apply what you said with 2 birds to 4. It's just however many you've got times the chance of getting one, and that will always be the average for a binomial. Totally awesome. Here's what I want you guys to do. I want you guys to practice this right now. Make this distribution for me, where X is the number of girls, and of course you know what the values of X are. That's how many girls we can have, correct? 0 through 4. So it's very much, Sarah, like the one you asked for so many minutes ago in the homework, 0 through 4. But the difference is this isn't 0.2, 0.2, 0.2, 0.2, 0.2. I want you guys to figure out what these probabilities are. Okay? So take some time right now, use the previous ones as a model for what we did, and come up with these probabilities. And as you're doing that, I'm going to wander around and share with you guys the program that I shared with this side of the class already. Then we'll come back and we'll revisit this one.